All right, I'm going to go through the paper that we've been working on with Abelay, it's not around, and Java. It's around the decentralized identity in practice, benchmarking. Decentralized identity in practice, benchmarking latency, cost, and privacy. So I'll start with some general introduction about identity. So identity, of course, is a complex concept that plays a central role in our lives. It's a collection of beliefs, characteristics, experiences, and values of an entity or person. It's also a dynamic construct, and that's how it's being treated in other, other areas of studies. Digital identity is something that we all have. It's a bit of a more complex array that is centered around specific identifiers that are unique data points that we use to label an entity or again, a person. It can be username, email, user ID. It has certain attributes that would be a certain data points that you can associate with an entity. And there is another aspect of it are claims. So there would be statements that this entity makes about itself or about anything else. And of course, the credentials, which is something that is used to prove that we have, prove authenticity of the claims themselves. And as far as digital identities are concerned, we have three models for digital identities. So we have a centralized model, where all the user data is concentrated in one place, in a repository, but it makes it highly vulnerable to any breaches for obvious reasons. Basically, users have very little control. We also have this federated identity model, where identity providers track users' usage. But of course, in this case, they are compromising privacy, and they are sharing this control over it. And then, in that case, the federated identity model is as strong as the weakest member of the federation. And the third, the interesting one, or the more interesting one, I should say, is the decentralized identity that shifts control to the users via cryptographic identifiers, credentials, which is enabled by the worldwide web, by the W3C standards. And that essentially changes this locus of control between users. So let's go for some key concepts related to decentralized identity. So first, DLD, the globally cryptographically verifiable identifier. It follows a certain standard format where we have a scheme, such as the ID, then a method, in this case, it's SOV, sovereign, and then the method-specific identifier. The DID documents follow a JSON structure. They contain a public key, verification method, service endpoints. They can be stored on-chain or off-chain. And we have DID methods that specify the rules for creating, resolving, updating, deactivating, or deleting DIDs on any particular network. There are also DID operations, so create, resolve, update, revoke, deactivate, delete, that may be executed. And they basically represent this whole life cycle of what's going on with this the DID. So moving on towards the experiment, we picked the three platforms that have different architecture, different architecture approaches. We've got Ethereum, which uses smart contract standard, where DID documents are reconstructed from contract event logs. We got Hedera, that uses event stream model, and the lifecycle events are published to the Hedera consensus service. However, the documents themselves are stored on-chain. And we also have XRDL that takes a ledger native approach, this XLS 40 standard that was introduced the ID objects. And it doesn't require smart contracts. So motivation for the research was to find a way to benchmark different systems, and also to ask, gave us an opportunity to ask 3 questions related to performance. So what's the latency, cost, and I guess privacy aspects, in the case of mental data leakage profiles for across these platforms for core operations. Which architectural choices and SDK workflows explain the observed differences, and which platform best balances responsiveness, cost, privacy, and the real-world deployment. As far as the methodology is concerned, we looked at 3 platforms. We tested the split-based reference case. We looked at latency, measured with Node.js high-resolution performance timers. We measured cost by looking at on-chain fees. We also converted it to USD, and we compared it in absolute terms and in relative terms, which I'm going to get to in a sec, and privacy by introducing this metadata decompositions. It's all been done with 100 iterations per each operation. So, as far as the results are concerned, we have here the absolute latency analysis. First thing to notice is that the resolution, the read operation, is fast for each one of them. We've actually Ethereum taking the longest, half a second. For write operation, Ethereum is basically takes around the same time as it takes for block time, with very high variance. XRPL is very consistent in here with 5 seconds, but it has a very, very tight distribution, which means it's very, very stable. And Hedera is the fastest one, although it has, I guess, a bit more outliers that are probably resulted from a result of a mirror node confirmation pipeline. And as far as the latency analysis, which is relative to this control, you can see that again, Ethereum has the highest absolute latency, Hedera has the fastest execution, and XRPL has the fastest consistency. I guess Ethereum's write operation aligned exactly with its block interval, which basically emphasized the fact that it's well integrated with its smart function. And then for XRPL and for Hedera, you can see that it's around 130 to 150% more defined, which is the result of the extra overhead related to non-consensus related operations. Cost analysis, on-chain operations on Ethereum are all around 6 cents. XRPL and Hedera are way cheaper. For XRPL, most likely because of the fixed fee model. When it comes to the relative cost analysis, we can see that Ethereum, again, is the most expensive because it's resource intensive, and because of all the on-chain operations. When it comes to XRPL, it's the lowest cost in almost perfect predictability. And Hedera has also very low cost with very moderate overhead. When it comes to privacy analysis, we took a slightly different approach. So we started looking at all the DID operations that are on chain, and thus, whenever this is done on chain, the transaction payload is visible to anyone. So we wanted to see what sort of fingerprinting is available, and what sort of fingerprinting is available for any, I guess, adversarial users to track or be given data points to determine So what we did, we used channel entropy based on the observable payloads. Essentially, the higher the MLS, the more leakage there is. The lower the MLS, the stronger the bounce. So first, we tokenized all the JSON files. We looked at the JSON files. We took all the tokens. We then computed channel entropy per token. And then we aggregated it in order to scale entropy by average tokens per transactions, and that resulted in the final cumulative MLS score, which was available to update, revoke, and delete operations on a data set of 100 transactions per each operation. And in here we can see that Hedera has the lowest leakage. Ethereum has the moderate leakage, and XRPL has the highest one. Even though bits per token are very low for XRPL, I guess because there are at least 30, well, there are on average 37 tokens in every transaction on XRPL. The total information leakage just adds up. So because of this more verbose payload, I guess XRPL just exposes a bit more information that may potential fingerprinting concerns. All three, we conducted an interoperability analysis as well, where all three methods comply with Worldwide Web Consortium DIT core specifications. Ethereum benefits from the most mature tooling. In this case, there are the strongest standard participations through decentralized identity foundations. And XRPL is newer, but again, very interoperable and selling with increasing standards. Key findings in here are that, of course, Ethereum has latency and costs. It offers very deep ecosystem integration. XRPL, on the other hand, delivers consistent, very low cost performance and very predictable. It exposes more metadata on chain, though, and then achieves the lowest latency and privacy, provides strongest privacy. The recommendation based on this analysis conclude that the event stream architecture with fast fidelity and the deterministic low fees would suit any solution best. Also, storing documents off chain and having this event on the log, so basically we can directly transactions from the beginning. It's more appealing. These systems are already in use or are being rolled out, especially in privacy preserving KYC, cross-border identity portability. There are those frameworks such as EIDAS, developed by the European Union, verifiable diplomas, DeFi compliance through wallet-held credentials, etc. Thank you.